So let's talk about another property of harmonic function, which is given as analyticity. Okay, so analyticity. What does it mean? Okay, first thing first, I guess all of you guys know what analytic functions are, but still, let us just remind ourselves what those are. So let's say, so just a small definition. Okay, definition of analytic function. Analytic function. Okay, so let's say f from omega subset of Rn to R is said to be analytic at the point x naught, in omega, of course, if f is infinitely differentiable at the point x naught, and there exists, and so let me put it this way, and it can be represented by a convergent power series in the neighborhood of x naught. Is this clear? So essentially, you see, it's not only C infinity function. Okay, of course, any analytic functions are C infinity. It's not only C infinity, but more. It is actually such a function which can be represented using a convergent power series expansion. Convergent, very important. Power series. So you can represent the function. Let's say if it is analytic at the point x naught, you take a small neighborhood of x naught. In that neighborhood, you can always represent the function with the help of a convergent power series. Okay, right. So that's analytic function. So what is the difference between infinitely differentiable functions and analytic functions? So just a small remark. Okay, this is just I mean, I am quite sure all of you guys all know this part, but still, just a reminder. So remark: there exists infinitely differentiable functions, differentiable functions which are analytic, which are not analytic. Okay, not analytic. Okay, and for example, you can just take this function. I'm not going to do this, but f from R to R, let's say, okay, given by, I'm not going to prove this thing. I mean, you guys can do it yourself if you are interested. So it's basically exponential 1 by x, let's say, yeah, and x is greater than equals to 0, and 0 if x negative. Okay, this function, I mean, you can show that this function, this is minor. Okay, you can show that this function is infinitely differentiable. Okay, but it is not analytic. So basically, one can show that f is infinitely differentiable at 0, but not analytic there. Okay, so one can show that. So that's the analytic part. What and please remember, whenever we are saying analytic, I mean real analytic. Very important. Okay, because you guys already know that complex analysis is a totally different thing. Complex analytic functions are, any holomorphic functions are basically analytic functions. Okay, so you don't have to worry about all these I mean technical details in a complex case. In a real case, There are C-infinity functions which are analytic, which are not analytic. So for example, this one. Yeah. Okay. So the property which I was talking about is this. So this is the property of harmonic function. Another property of harmonic function. Now this thing for this course, what I'm going to do is I'm going to skip the proof of this. Yeah. So this is called analyticity. It says that, so this is another property. It says that let U is harmonic in omega. Okay. Then U is analytic in omega. Clear? So basically what am I saying is this. Initially you have seen, so let me put it in a small note. We know that any harmonic function is infinitely differentiable, right? A harmonic function is infinitely differentiable. Okay. This we have proved, infinitely differentiable. Now what this property says is, it is, so what the above says is it is not only infinitely differentiable, but one can represent any harmonic function as a convergent power series, in a neighborhood. This is how do I put it? In any neighborhood of x naught containing omega. So essentially, if it is harmonic, you take any point x naught in omega and you take a neighborhood around that point. You can represent any harmonic function with respect to a convergent power series expansion. Clear? Okay. So very, very important. It says initially we have seen that harmonic functions are only infinitely differentiable. Here we are saying that it is not only infinitely differentiable, but it is more, that you can represent any part of the function, yeah, with respect to, I mean, you can represent it with the help of a convergent power series. Yeah. Okay. The proof of this thing will actually, so proof, I mean, we will not do the proof. I'm just giving you some ideas. What we need to do is we need to use the estimate. Yeah. If you remember the estimate on derivatives, this we have to use the estimate on derivative, and with the help of this we want to, and plus some Taylor series expansion. Okay. Taylor series expansion. So as I have told you earlier, we are not going to prove this particular theorem for this class, okay, for this course. But the thing is, if you are interested in the proof, try to do it yourself. So essentially, it's not a very, very difficult proof. You just have to use the derivative, estimate on derivative, and our Taylor series expansion. But I am not in any way suggesting that this is going to be a very, very easy proof. It is not a very easy proof, okay. And I am going to skip this property for now. But the thing is, please remember this thing. Whenever you are talking about a harmonic function, a real harmonic function, they are always analytic. Yes. So basically, they are C-infinity function and can be represented with respect to a convergent power series expansion. Okay. Now, what we are going to do is we are going to prove another property of harmonic function, which is called a Harnack inequality. Okay. This is extremely important. This is one of those, star properties. Okay. Let me put it again like this: star properties, very, very important property. So Harnack inequality. So what does this say? So essentially, this actually compares the value of a non-negative harmonic function. Okay. So essentially, why is this important? So basically, this says that the values of a very, very important, this one, non-negative negative, yes, important. Without this, it won't work. The value of a non-negative harmonic function is comparable. Okay, this is what it says. Vaguely. So whenever you think of Harnack inequality, just think of it like this. It is saying that if you are giving me a harmonic function, yeah, I don't care what sort of function is it. At least if it is a harmonic function, if it is a non-negative harmonic function, this is very important. Non-negative. Without this condition, it won't work. Okay, if it is a non-negative harmonic function, then the values of the function on a domain omega, okay, they are comparable. Okay, so what is the theorem? Let's just write down the theorem properly. So it says that for any open and connected set, okay, V which is contained in omega u, there exists a constant C positive such that, so of course depending only on V, depending only on V. Okay, so you fix a V which is compactly contained in omega. Okay, and depending only on V such that the supremum of U, okay, supremum of U over V is less than equal the infimum of U over V. Okay, and this holds for all non-negative harmonic functions, U in omega. Clear? Okay, here there are some particular things which I want you to understand. Okay, the one thing is this: whenever I am writing V is contained, so some notations which I need you to understand is this notation. Okay, so first of all, I am saying V is compactly contained in omega. What does that mean? Let's just understand that V is compactly contained in omega. This means compactly contained. Compactly contained. Okay, what it says is this: it says that, so here I'm just writing V, you can just take anything you want. Okay, so essentially whenever I'm saying it is compactly contained in omega, what I mean by this is V, of course V is contained in V bar, right? That is always true. V is contained in V bar. This implies V is contained in V bar, and that will be contained in omega. Is this clear? This implies this, that V is contained in V bar. So V bar, see, this is, again, whenever we are writing this thing, we always assume that V and omega are open. Is this clear? We are always assuming V and omega are open. Just think about it for 5 seconds. What I am trying to say. Think of omega open, V open, and V bar is such that V is contained in V bar. Of course, this is always true, but such that V bar is contained in omega. Okay, take 5 seconds. Think about what I just said. So I am quite sure you have more or less some idea now that what exactly does it mean. See, essentially it means that it will be away from the boundary. So essentially what it is saying is the V bar, yeah, V bar. So just think of this as this. Let's say this is bounded. Yeah, if it is bounded, if V is bounded, or let's say omega is bounded for now. Yeah, just for example, let's say omega is bounded. Okay, example, omega is bounded. Yeah, then V bar is closed and bounded. Yeah, that will imply V bar is compact. Okay, So basically, it's a compact set which is contained in omega, right? So there is some distance between these things. So in this case, so therefore, V is such that is an open set such that V bar is contained in omega. Yeah, omega is an open set, V bar is a compact set. So essentially, you can think, I mean, you do realize that there is a distance between those two. Okay. So essentially, it is quite V is quite comfortably inside omega. You can just think of this as vaguely. This is what it says. Okay. Right. Now let us talk about another small details which we are going to prove here, and that is called I mean the small idea which we are going to write it down here. So this is called the supremum. Okay. Here I am writing sup, right? Here I am writing the supremum, and what does this say? See. Here I wrote sup of u and inf of u. What does that say? Let's understand. This is the first notation, the second notation. Supremum of a function f. Yeah. So this is basically supremum of f. And whenever I write infimum of f, it means that it is infimum of f. Clear? So what is the sup and f? Sup of f and inf of f. Sup of f is the supremum of f. Inf of f is the infimum of f. Right. So once we know this, what we are going to do is we are going to start with the proof of this theorem. So essentially, let's say we start with the proof. Okay. Let's start with let R be defined as the 1/4 times the distance between x and the boundary. Clear? Okay. So essentially, we are proving the Harnack inequality, and what we want to do is this. Let's say that's your omega, okay, and x is such that the distance between x and del omega. So I'm taking r. So let's say this is x, yeah. The distance between x and del omega. Let's say this is your the distance between x and the boundary of omega, and let's say that is the r, the 1/4 distance. R. Now you choose x and y in V such that mod x minus y is less than r. We can of course do this, right? So essentially think of x in the center, and you can choose a y which is inside the ball of radius r, something like this. Okay. Then by mean value theorem, what can you say? You can say that u of x equals to bx to r, okay, u of z dz, right? This is mean value property, okay, because u is harmonic inside the omega and v is contained in omega, right, and does not touch the boundary, so it is away from the boundary. So this is this, and this I can write it like this. Please try and understand what I am doing. I will explain, but for now, just try to understand this one. P y r u of z dz. Okay. See, what am I doing is this. This notation, I'm just writing it together. The integral over the ball that can be written as 1 by alpha n r power n. R is 2r here, so it is basically 2 power n r power n. This I am writing, and here I am dominating this integral of bx to r of u by dominating byr with bx to r, integral over byr with integral over bxr. Why I can do this? Because you see here y of r, this is a smaller ball, right, than bx to r. Bx to r is a much bigger ball, and since byr is contained in bx to r, right? If we take x minus y to be less than r, of course byr is contained in bx to r, right? And this is again contained in v. Of course, this is contained in v, which is again contained in omega, right? So I can do this. Since this set is bigger, the integral of this set is always getting to be, will always dominate this, right? Okay, so that is there. Now this can be written as 1 by 2 power n, okay, integral b y r u of z dz. Yeah, I can always dominate it like this. I'm just writing this notation like this, and I'm taking the volume inside. Okay, so that is equals to 1 by 2 power n, and what is it? This is u of y. Okay, so for any x y, you have u of x, any x y such that this happens in v such that mod x y x minus y less than r, u of x is greater than equal 1 by 2 to the power n u of y, right? Yeah. Now interchanging x and y. Of course, we can do this. Yeah, there is nothing special about x and y here. So I can write u of y can always be greater than equals to 1 by 2 power n u of x. Yeah. Hence for all x minus y, or for x y in v such that mod x minus y less than r, we have 1 by 2 power n u of y less than equal u of x, which is less than equal 2 to the power n u of y. Okay, right? This is always true. Okay, so once this is true, now we are basically done. So now since v is connected, now here one thing I am using, please remember, see, we have assumed that this is a non-negative harmonic function. See, I said it holds for all non-negative harmonic function. Huh? Do you know where am I using non-negativity here? This here non-negativity is important, okay? Because otherwise this may not be greater than equal this. Okay, right. Now since v is connected, this is also important. Huh? Since v is connected and v bar is compact. Okay, why v bar is compact? Because you remember what I said is u is contained. So this is the definition. Huh? V is compactly contained in omega. It means that essentially v is contained in v bar, which is bounded and is contained in omega, right? V is contained in a compact set v bar. So it means that I didn't write it. Okay, I didn't write it, sorry. So we have to write it compactly contained. So basically compactly contained is v is contained in a v bar which is compact and it is contained in omega. That is called a compactly contained set. Okay, maybe I can write it here. Sorry, somehow I skipped it. So v is contained in a, so omega can be any set, doesn't matter. Omega doesn't have to be bounded, but v is contained in an compact set which is contained in omega. This is what it said. Okay, right. Now, so since v is connected and v bar is compact, here v is compactly contained in omega. So v bar is compact, right? V bar is compact. Compact set, what we can do, we can actually cover it with a change of there are finite cover, right? There are finite covers. Okay, so let's say we can say there exist finite covers of balls, okay, bi's, okay, and this is I equals to 1 to, let's say, n, okay, of radius r by 2 such that bi intersection bi minus 1 is non-empty. Of course, we can do that. See, essentially what am I doing is this. This is why compactly contained is very important. Otherwise, we can't do this. Compact, since see, omega can be anything, right? It can be bounded, it can be unbounded. But whenever I'm saying it is, this holds, this property, you can compare the values of a harmonic function in a v bar. It basically says that you just don't look at the whole domain. just concentrate on a part where it is compact. Okay, concentrate on a compact part, V bar, and in that part we can do this. So that is why, since V bar is compact, you can have a finite cover, right, like this. Huh? That bi intersection bi minus 1 is not equals to phi for I equals to 1 to n, of course, and this bi of radius r by 2, that will cover the whole V bar. Huh? Okay, so then what happens? Then if this happens for any xy less than equal, here you see, for any xy less than equal r, we have proved that this sort of property holds, right? Ui greater than equal, so ui and ux are comparable. Yeah. So then what you can say is ux is greater than equals to 1 by 2 to the power n plus 1, because for every by this is happening. Okay, so ux, it will just get 1 by 1 if you just go on 1 by 1 for every xy. See, x and y, if it is here and here, y connectedness is required, because otherwise you can't connect these two points, right? Now you just take balls overlapping this thing. Okay, do it like this, and after that, after a finite number of points, what will happen is, so let's say n, capital N is that finite number of points. What will happen is you can cover the whole thing down. So, and for every xy in between these two, you have this property that u of x and u of y satisfies this two property. So for any xy in V, so for any xy in V, okay, you can just write ux is greater than equal 1 by 2 or n plus 1 u of y, and simultaneously the opposite is also true. So u of x to the power n plus 1 times u of y, that is also true. Okay, so once this happens, this holds for any xy in V, and hence we can say that we can compare x and y. So and hence one has that the supremum of Vu over V is less than equal some constant times the infimum of U over V. Clear? Okay, and this C of course depends on V. So is this clear? What am I saying? Because you see, if you take the supremum here, supremum of U is always going to be dominated by this, right? Okay, and then you take the infimum on both sides, so that nothing will change, so it will remain the supremum of U, and that will be less than equal some constant times the infimum of over V. That's all. Okay, so that is why what we are saying is the supremum of U. So you cannot be, you see, this actually gives you, so this is the quite so this illustrates, this property illustrates the mean value property of harmonic functions. See, what mean value property says is basically in a small ball kind of thing, you can actually average out the value of U, right? That's what it is essentially saying. Here also it is saying the same thing. So basically, let's say in a small compact set, if at one point U is like an infinity and one point it is very small, then the average won't give you the value of U at some other point, right? You understand what I'm saying? For the average thing to work, U has to be quite, homogeneous in its boundary, in the neighborhood. So that is what it is saying, that you can compare U, the value of non-negative harmonic function, okay, in a compact set. You understand? In a compact set, you can compare the values of U. That's what it says, and it is one of the most important properties of harmonic functions. Yeah. So with this, we are going to end this video.